Welcome you all back to the subject of industry engineering and management. This video will be continuing with what we have been discussing in the previous unit 4. The topics which have been marked in red are the ones which we'll be seeing today. Single sampling, double sampling, multiple and random sampling, concept of OC curve, which is also called as operating characteristic curves, AQL, AOQL, producer's risk and consumer's risk. What is simple random sampling? In the previous video, we have seen about what sampling is about, sampling population, what does lot size refers to, and what does sampling unit and sampling element refers to. So simple random sampling is a process where it is one of the most straightforward probability of sampling strategy. It is a method for choosing a sample population from a wide range of options, right? So in simple random sampling, each member have the highest population of being chosen as the part of the sample. You could see here there are closer to 12 or 14 members out here. Randomly, you just take people without even looking into any consideration, right? A good example is a faculty or a teacher who is randomly calling someone in the classes to speak about or is questioning someone in the classes, which is pure of a random sampling concept, right? And the second strategy of sampling is systematic random sampling. In systematic random sampling, what we usually do is we take the samples in a systematic way, where you first calculate and fix which is the sampling interval you are going to choose. Whether you are going to choose interval in terms of time, whether you are going to choose interval in terms of numbers, it is purely different upon the person who is doing it, right? So the number of elements in the population divided by number of elements needed for the sample. That is how you are going to be choosing the sampling interval. So once you choose the first starting point, which is of course a random starting point between 1 and the sampling interval, you have to ensure that the next set of sample is taken with the same interval. Right? So that is how the subsequent samples is taken. Example here refers to the same number of 10 persons, and you are going to take a person from in terms of even numbers, right? Person from 2, 4, 6, 8, you're going to take them into consideration. So these persons, which is every second person in this particular population, is taken for sample, right? So that is how you systematically you select the sample. In an industry perspective, it also can be like you take the sample from a person who is working at 10 o'clock. From the same person, you take a sample at 12. You take the same person a sample at 2, right? For every 2 hours you are taking. Also you can take in terms of days. If you're taking a sample from person X on Monday, you can, and if you're considering that to be every second day, Wednesday you have to take that sample, and Friday you have to take that sample, right? So that is what your systematic random sampling refers to. The third category strategy of sampling is stratified random sampling, where the entire population is categorized into smaller groups, which is called a strata, and from there you are going to choose a particular set of population, right? So you'll be considering them as your sample. Now, say for example, how do you categorize them? It is based upon the attributes or characteristics. It could be like income of the entire population or educational attainment, right? Of course, we have been many surveys we would have entered in our through Google forms and other things, right? Many persons are asking like, what is the kind of requirement you expect in a particular kind of product, the feedbacks that you will be giving. That is, you segregate that, right? You segregate that as age from person 18 to 20 or 18 to 30. A good example is if you wanted to get a feedback about a newly launched mobile phone, then of course you can get those data from a person from 18 to 30, or probably 18 to 40 in the range. And you can also categorize them depending upon the purpose. Like students, you can categorize them, or you can group them as persons who are working, or you can group them as persons who are doing businesses, right? So that is the set of strata you can classify them. So stratified random sampling is about choosing the person from the entire population based upon certain attributes, and then grouping them, and then taking them as the sample. Now we'll see about the various sampling plans which are through which you can go for your inspection. The various sampling plan is specified by the lot sizes, the sample sizes, the number of samples, and also the acceptance or rejection criteria. It is purely about two categories. One is the attribute sampling, other one is the variable sampling. It is, as the name indicates, attribute sampling. The sampling is more focused towards data which are it's about attribute data, right? So variable sampling, it's about sampling technique used for variable data, and we have discussed in previous videos about what attribute and what variable is about, right? As the name variable indicates, it keeps on varying over a period of time, and attribute data is something which is very fixed, right? So it is about taking a yes or no decision, or probably your and or gate in your electronics, like 0 and 1. That is what your attribute data is about. So what is single sampling refers to? Single sampling, you are going to take a random sample from the lot. So the sample is going to be n, and then you are going to find out the number of defectives in the sample. And if you see that if the number of defects does not exceed the C, which is the acceptance number, you are going to choose to accept the lot. If in cases you find that the number of defectives is exceeding C, then you are going to reject the lot, right? So that is very simple. It's purely about single point decision making. If D is greater than C, you accept it. Sorry, if D is less than C, you accept it, and if D is greater than C, you're going to reject the lot. But what is the shortcomings or limitations of single sampling is that there are more possibility of a good lot getting rejected, right? So that is the reason, and another sampling plan called as double sampling plan has been defined. So what it gives you is it gives you second opportunity to take a second set of sample from the lot. So how do you measure this, or how do the decision is taken here? You're going to take a first sample size of n. It can be a random. You can choose the sample from a random way, and the number of defectives is down counted. If and you compare to the sample's acceptance number A1 and rejection number, and you are going to denote the number of defectives in the sample 1 by D1 and in sample 2 by D2. That is how you are going to defect, right? So it is about having two acceptance number for a first set of sample. If you're taking a sample of size n, which means it's the size of 10, and then you have to have an acceptance and rejection number. Maybe if you're going for if you're expecting for 90% of acceptance number, the number of sample size of 10, then rejection number, the acceptance number has to be 9 and the rejection number has to be 1. And for the second set of sample, either you can go for the same size or you can go for a different size too, right? So if you're going for a different size, obviously the rejection number and the acceptance number keeps on changing, right? Depending upon the type of percentage you wanted to achieve, the acceptance number and rejection number also keeps on changing. So that is denoted by A2 and R2. And the defectives in sample 2 is denoted by D2. Now we'll see how a double sampling plan works. So the number of defectives in the sample is denoted as n. So once you take the defectives from first sample, and if you see that it is not exceeding the C1, which means that it is not exceeding the acceptance number, you are going to accept the lot. But on the other hand, if you see that it is equal or exceeding the rejection number, then you are going to reject the lot. So once there is a case where both of the scenarios are not happening, which means that the defectives is exceeding C1, but it is lesser than the rejection number, you have to take the next sample. But when you see that it is also exceeding the rejection number, right? The acceptance number and rejection number can be quite different. If your acceptance number is 6, you can accept up to 6, but your rejection number is not more than 8. And if you find that the number of defectives in the sample is 7, which is exceeding C1 but lesser than R1, then you are going to take a second sample of N2. Right? So once you take the second sample, you will be finding the number of defectives from the second sample. From the second sample, if you see that the number of defectives is exceeding C2, the acceptance number is for the second sample. You are going to accept the lot, and if you see that it is equaling or exceeding C2, if it doesn't exceed, you will accept. If you're exceeding C2, you will reject the lot. So it is a kind of second innings in a test match, right, where you have the opportunity to ensure that you meet your required objective by using a second opportunity. So double sampling plan is about taking about two samples and considering whether to accept and reject the lot based upon the number of defectives. The third type of sampling is your multiple sampling. Multiple sampling is almost similar to double sampling plan, but the only difference being is that here you will be having 3 or more samples. Before you take a decision, you will go for 3 or more samples to check whether the lot can be accepted or not. And no final decision is taken at any stage. It's only at the end of the stage, and you will take the final decision. It's not that at the first stage you will be taking the decision, nor at the second stage. If you're going to take 3 samples, then if you 3 or more samples, then at the end of the sampling, you will be going to take the decision. A sequential case sampling is a kind of an extremity where which is very lesser to occur, or it's an extreme case of multiple sampling where the sampling might continue until the lot is exhausted, which means that you find that uh, all the lots, all the entire components in the lot have been inspected. It's almost like you every product is taken out for inspection, right? So it calls for inspection on item by item basis. So only after each of the every items in the lot is inspected, the decision is taken whether to be accepting or rejecting the lot. So, and the sampling keeps on continuing, but it is, of course, it's almost similar to what your 100% inspection is about. Next, we'll be seeing about the important concept of OC curve, which is also called as operating characteristic curve. So it is one of the key important topic in sampling. And before we move on to the actual OC curve, there are a few terms which needed to be known. First one is AQL, which is called as acceptable quality level. What does it indicate? It is a maximum percentage of defectives as defined by the producer, right? It is the maximum level which the producer, the maximum percentage of defectives which is the producer can give out. Now, what is LTPD? I'll come to this alpha and beta separately. Now, what is LTPD? LTPD is a lot tolerance per defective, which is the highest percentage of defective items that can be considered acceptable in a batch. Now, what is LQL? AQL is acceptable quality level, LQL is limiting quality level. So, which is the percentage of defectives which defines a consumer's rejection point beyond which the consumer will not accept. Right? There are few see. A good example is you get your shirts, right? Maybe all your shirts are not completely satisfied, or not all the requirements of the customers are not completely satisfied. Sometimes you feel that maybe the color of the buttons could have been different, or might be the logo which have been imprinted could have been imprinted on the other hand. So right, so that is considered to be a minor defective, right? And some of the example can be, some of the shirts have an additional buttons at the bottom, right? A few of the brands do not have that. Even you consider that to be defective, but this is acceptable from a consumer's perspective, right? They are not looking up to these to be a most critical aspect of the product. These minor defectives are not going to affect the consumer's perspective of accepting the product, right? So that is the maximum percentage of defectives which the consumers consider to be accepting, beyond which the consumer will not accept it. If, say for example, there are no buttons, if you are supposed to have 6 or 7 buttons, and if there are only 4 or 5, then the customers will not be accepting it, right? So that is the limiting quality level, the percentage of defectives which defines your customer's rejection point. Now we'll see what alpha and beta is about. Probably we'll discuss that with the OC curve. Maybe that will give you much more an easier conceptual of understanding it. Now this is what your OC curve is about. You have your percent defective on your x-axis and probability of acceptance on your y-axis. What the ideal OC curve has to be like this. It's for every sampling. You could see that the number of the percentage of defective keeps on increasing. You could see that the probability of acceptance also keeps on declining, which means in an ideal scenario, if there is 0% defective, there is 100% of acceptance. That is the ideal scenario. Of course, an ideal scenario is highly difficult to achieve. So you consider there is how an operating characteristic curve for any sampling or inspection is done. This is the OC curve which will be followed. You could see here two categories. One is AQL, one is the LTPD, which is acceptable quality level, and lot tolerance per defective. We have seen about what LTPD is about. Highest percentage of defective items that can be considered as acceptable in a particular batch. Now, what is this alpha? Alpha is, now you are expecting 95% of acceptance. From the inspection, the objective of the industry is to have 95% of acceptance, which means that from 95% you will draw a line, and correspondingly you have to ensure what is the maximum percentage defective you could accept here. So this is called as the producer point, and this deviation of 0.5, the 5% which is 0.05, is called as the producer's risk. Producer's, what does producer's risk refers to is, producer risk is the probability of rejecting a good lot. Now, if by chance your lot comes into this category of 5%, then the probability of that particular lot being rejected will also be present. Now, what is consumer's risk? Consumer's risk is the probability of accepting a bad lot. Now, where does this consumer risk? This is your consumer risk. You could see that beyond this particular, now say for example, the consumers say that if it is not less than 10 percentage of, or not more than 7% defective, we won't be accepting. In this case, not more than 15% of defective, we won't be accepting. So which is the maximum percentage. That is why you mark your LTPD there. This is purely upon the requirements of the consumer. Now this is the requirement or the objective of the industry, the 95%, and the probability of acceptance you fix, right? This is where you draw your 95% line, and this is depending upon the consumer's requirement. Consumers say that not more than 15% defective we may accept. So this is the maximum percentage of defectives which can be accepted in a lot. Now what does this refers to? The area beneath this. This is called as beta. This 10% possibility is there, which is called as the consumer's risk. What does this 10% represent? The 10% refers to the probability of the consumer receiving a bad lot, right? So this is a probability that the consumer might receive this 10% of bad lot. On the other hand, there is a 5% probability that the producers may lose a good lot, right? So an ideal balance has to be maintained to ensure. So a good sampling plan should ensure that the result of the sample, that is what we have seen in the previous video, characteristics of a good sampling plan. The result of a sampling should ensure or could be easily applicable to the entire population in general, and it should give the overall picture to the industry, right? So why it is very important is because it provides a trade-off between all the parameters which you have seen: the sample size, the lot size, the acceptance number, the consumer's risk, and the producer's risk. And it helps you to determine whether the particular batch meets the required specification, which is quite often difficult to assess, right? Because there are so much of strategies which distinguishes between acceptable and defective units in intermediate levels. So that is why OC curves will give you a clear indication about whether to accept the lot or reject the lot. And it also has that limitation that there is a producer's risk which is called as an error, and there is a consumer's risk which is also an error of receiving a bad lot, and the producer's risk which is a probability of rejecting a good lot. A sample OC curve is displayed here. So under this sampling plan, if the lot has 2% defective, then you could see here the requirement is 2%. If the requirement is 2%, you could see that the probability of accepting the lot is 92%, right? So only 2% of defective is acceptable. That is what the company has decided. So for a 2% defective, you could see for an ideal OC curve that the probability of acceptance will be 92%, and the probability of rejecting the lot is 8%, right? So that is what this 8% is called as your probability of rejecting the good lot. If the lot has 10% defective, right, that is what has been denoted here. It has a small probability of being accepted. The probability of rejecting the lot is 89%, right? That is what has been displayed here. If there is 10% of defective can be accepted, then which is called as LTPD, lot tolerance per defect. Now this is your AQL, which is acceptable quality level, and this is your LTPD, which is your lot tolerance per defective. If it is a 10% defective is accepted, then there is you could see that the probability is almost closer to again 11% of being. The probability of rejecting the good lot is again 90%. For 10% defective, the probability of rejecting the good lot is 89%. Most consumers understand that 100% inspection is impractical, and they are accept that there will be a certain level of defective which will be produced. So the acceptable quality level is the percentage the customers is willing to accept as good, right? And whereas LTPD is the upper limit which you are going to fix, beyond which there is no possibility that the customers will be accepting that particular lot. Whereas on the other hand, customers also want the lot to be with the quality of the lot to be better than or equal to AQL, but of course they are not going to be compromising on the quality, hence why they do not want any lot or batch size to be as poor as your LTPD. But on a more ideal scenario, they even do not accept the lot which is as equal to LTPD. They have to be having a good lot which is more than your LTPD, which means that the maximum value in it has to be very lesser to the maximum value, right? That is what the LTPD is about. So they do not want to take a risk of accepting a lot even if it is on par with your LTPD value. Like you could see here, even if it is on par with LTPD, they do not accept the lot, they will be rejecting the lot. If it is probably lesser than the LTPD value, then they will be accepting the lot. So how do you define a good and a bad lot? As you could see, the OC curve, the ideal OC curve is this. So if all the lots are falling within this particular range of AQL, you call them to be a good lot. When the lots are falling beyond this LTPD, you call them to be a bad lot. But of course, this particular scenario is where most of the lots will be falling. That is what your normal distribution curve also refers to, right? Predominant of your measurements comes into that bell-shaped curve. You usually have this bell-shaped curve, right? So that is what your normal distribution curve refers to. So predominant of your values comes in the range of between AQ and LTPD, which indicates that of course the quality is not that good, and on the other hand, but it is not that bad to reject it also, right? So that is of instead of defining that to be good and bad, we'll define as really good, really bad, and the third condition where it is okay, but it is not of that greater quality, right? And the producer's risk is the probability of acceptance is rejected. If it is falling within this range, the lot is falling within this range, then the probability of that lot being rejected is higher. Of course, the consumer's risk again comes as a beta, which is the probability of acceptance of a bad lot, probability of accepting a bad lot. That is what your consumer's risk beta is about. And next we'll be seeing about AOQ, which is average outgoing quality. What is average outgoing quality? It's the average of rejection percentage, like the average of rejected lots and the accepted lots from the set of samples which have been inspected. So how do you calculate it? Probability of accepting a lot multiplied with the fraction defective in the entire lot which you have taken, multiplied with the difference of lot size and the sample size, and it's also divided by n. So which is a probability of acceptance multiplied by small p into n minus n divided by n. That is how you measure your AOQ, which is average outgoing quality. So the result of this acceptance sampling, assuming if the lots are 100% inspected, it adjusts to the quality of the lots being inspected, right? So the maximum outgoing quality level, which is which is the maximum outgoing quality level, is referred to as AOQL. What does it indicate? It is the highest level of acceptance which can be obtained from the inspection. That is what your AOQL refers to. So how do you create a sampling plan? So a sampling plan is first you will be determining what your AQL is about, what is acceptable quality level. It can be for minor, major and critical defects. So in general, for a critical defect, the AQL is 0.1, and for a major defect, you consider to be 2.5, and for a minor defect, it is 4. So once the sample, the AQL level is determined, then you will determine your risk factors, the alpha, beta, which is called as the producer risk and consumer's risk. So once you determine this risk, like how much of percentage there is a possibility of risk, because from a manufacturer, you always want all the products to clear the inspection, right? If you produce 100 batches and you see that only 90 batches are moving out, then the 10 batches are considered to be loss for the manufacturer. So in an ideal condition, the producer do not want the risk of rejecting a good lot. So of course, on a practical scenario, he also knew that there is a possibility there. So he need to fix that percentage. How much of percentage is considered to be a producer risk and how much of percentage is considered to be a consumer risk. Once that is done, the third one is you have to choose the type of data. What is it is a variable data or an attribute data for a particular sample, and then you determine the overall population, the capital N, and from that you determine what is the sample size, small n. One, and again you fix up your defective rates D, and the acceptance number A, or we also call them to be a C, right? And the ratio number R is also to be determined. So it's a step-by-step process where first you fix up the quality level. What is the acceptable quality level you can give? Second thing is you fix up your risk involved, consumer's risk and producer's risk. Third thing is you determine what is acceptance number, rejected number you can have for the sampling inspection. So once all these things are done, then you choose what is the type of sampling you are going to follow, be it a single, double, multiple, or random sampling, which is the type of sampling you are going to follow. That is going to be your next step. Once that is done, the final step is going to be implementing that and taking the results. From the results, you can analyze the data and come to a conclusion, right? So thank you. We'll stop with this. We'll continue the remaining topic in the next video.